So let's let r of t equal a vector valued function ti plus t squared j plus 3tk. Let's go ahead and find a sub t, the tangential scalar component of acceleration, and a sub n, the normal component. Usually the easiest formula is the dot product formula. So, okay, if we write it down, if we want a sub t, then that's the acceleration vector a dotted with the unit tangent vector t. So you write the formula down, and it tells you what you need to do. It screams at you, find the acceleration vector, and also find t. And then the dot product is almost an afterthought. That's the easy part, right? So, in order to find the acceleration vector, we first need v of t, which is just r prime of t. So what is that going to be? I plus 2tj plus 3k. Keeping it simple here. So then what's the acceleration vector if you take the derivative of the derivative?
2j plus k?
Oh, just 2j, right? Because both I and k components are constant. So you take their derivative in v of t, and then you take their derivative, they're gone. Okay, so a of t is just 2j. Now we need t. Oh, wait a minute. What you want to get in the habit of memorizing what you have to memorize and not memorize anything else. So you got to know what a of t is. Oh, that's just taking a couple derivatives. T, you just flat out got to remember, flashcards, good way to do it. It's r prime divided by magnitude r prime, or v divided by magnitude v, same thing, right? So we've already got part of that. We've already got v, right? What does this formula tell? Let the formula tell you what you need. Let the formula tell you the steps. What does this formula tell you you need? You already have v on top. You need the magnitude of v. Oh, so you just look at this and take the magnitude. What do you get? Square root of? So yeah, we square this, we get 1. So we get, let me do the 4, let me do this in front. 4t squared, right? From that component. And then you get 1 squared plus 3 squared. So 10. Does everybody see how I came up with that? So what's t equal to? Well, out in front, we could write 1 divided by that square root, 4t squared plus 10, times essentially v, I plus 2tj plus 3k. So that's t of t, right? So then, well, I've got a of t. I've got t of t. What do I do? Let's dot them together. So let's say this. A sub t. All right. Now, first of all, don't scalar multiply out that 1 over the square root. Just leave it out front, right? So if you leave it out front of the dot product, you could pull it all the way out front. Then you can focus on just the components that matter. Now, if a of t is just equal to 2j, what does that mean about the I and k components? They're both 0. So when you take the dot product, are those components going to give you anything? No. If you multiply 0 times 1, you get 0. 0i, right? From the acceleration vector. If you multiply the k component, 0 times 3, you get 0. The only multiplication that matters from the dot product is what we get when we multiply the j components together. So what are we going to get from that? So do we want to include the j? It's a dot product, so it's going to be a scalar. So just for t, right? Okay. Does everybody see how I came up with that? All right, so I would want to write it like this. 4t over the square root of 4t squared plus 10. So that's a sub t. What's going to be the easiest formula then for finding an? A sub n, we're going to use the formula magnitude, acceleration vector squared minus a sub t squared. This is essentially the Pythagorean theorem right here. So we're going to take the square root of the magnitude of a squared. That's the magnitude of the acceleration vector, right? Minus what we just found squared. Does that make sense? All underneath the square root. Does that make sense? So we fill that in, big old square root. And okay, well, magnitude of a, the acceleration vector isn't too hard to find. What is that going to be? Well, the magnitude is 2, and then you square it and you get 4. Sure. Okay. Minus, okay, what do you get when you square this guy? 16 t squared over 4t squared plus 10. The square root goes away. Everybody believe that? We should probably do a little bit of algebra on this, simplifying, right? I know, no fun, but. So the common denominator is just going to be this guy. Okay, so big old square root. So I need to multiply this 4 top and bottom by that denominator, which is going to make what in its numerator? 16t squared plus 40. And then I'm going to put it all over the common denominator. Don't forget the minus 16t squared. So I'm kind of doing it all at once there. Does that make sense? Okay, then we have 16t squared minus 16t squared, which this is going on underneath a radical, which gives us underneath the radical 40 over 4t squared plus 10. They share a common factor. What do we get when we take out the common factor of 2 and slash it? So 20 over, underneath the radical, 20 over 2t squared plus 5. Would you buy that? Okay. So there's a sub n. Let me back off the view so you can get. Okay, so there it all is. Okay, so here's the picture. We've got the curve in white here. It's actually a parabola in space, and think of that parabola as the path on which an object is traveling, like a spaceship. It travels along this parabolic path. And r of t gives the position of the object at time t. So down here I've graphed the vectors we're interested in. The acceleration vector, a, that's in blue, a sub t in purple, and a sub n is in red. Now, the graph is kind of interesting because the acceleration vector is constant. But if we let the parameter increase, you'll notice that the vector in purple, a sub t, and the vector in red, a sub n, are certainly not constant. Oh, by the way, they do lie in a plane, all three vectors. At least it looks like, from this particular example, it looks like they lie in a plane. I've graphed part of that plane here for you. And so if these three vectors lie in a plane, certainly n, t, and a lie in a plane. So at least that idea is believable from this picture. Now, look, as the parameter little t increases to 0 from the negative direction, look at what happens. Both a sub n and a sub t change in length, but notice that a sub t really changes a lot. In fact, it's shrinking. Oh, and one other thing you should notice is that it's pointing in the opposite to the direction of motion. So here's the unit vector in the direction of motion t, and in green here, and a sub t is opposite. It's pointing in the opposite direction to t. And that means the object is slowing down. It's decelerating. Now notice, as t continues to increase to 0, whoops, let me get rid of this vector in green here. As little t increases to 0, the purple vector shrinks completely. And the red vector will completely match, at least at 0. I'm almost at 0 there. The red vector, a sub n, will completely
line up with or coincide with A, which means all the acceleration is perpendicular to the direction of motion. So you can see that here. And then as t continues to increase, little t that is. So by the way, a sub tt completely disappeared, if I didn't make that clear, when little t was equal to 0. But as t increases, little t, a sub tt reappears, and in fact it's pointing in the direction of motion, which means the object is accelerating. And this is all the while the acceleration vector a is remaining the same length. You can see so there you go. There's a nice picture of this particular example and these three vectors that help us analyze motion.